Hey guys, so we are starting into this Unit 10 with sequences and series. And so for the first day, what we're going to do is a pre-scale unit. A lot of this you may or may not have seen, so we're going to work on it to make sure we understand it. So here in this essential questions kind of going on, these, if you want to talk about together, we can to really make sure you understand them. But I want you to answer them on your own if you can try to do that for me. So objectives today, we're going to simplify factorials, change the starting value of summations, determine if a sequence is always decreasing or not, and try to reduce some exponents. So here, let's just talk about what a sequence is. So a sequence is going to be when we, this is plugged in, it's not quite working yet. Come here, you. Okay, I think I got it now. Yay! Okay, so a sequence is going to be where we can see that the terms are going up by like a constant amount, that's arithmetic, or down by a constant, again, that's arithmetic. Or we're multiplying or dividing by a constant amount, that's geometric. But we're seeing a pattern. So that's what we're going to talk about when we talk about a sequence. If we can see that sequences, as we keep going and going and going, if they are getting closer and closer to a value, then we say that the sequence has a limit. So if you guys remember my joke, we had 1, then 1/2, then 1/4. So this is geometric, where we're dividing by 2 each time. Then 1/8, then 1/16. This limit we can see as these terms keep going, this term way out here is going to be really close to 0. Not 0 itself, but super close. So that limit would have occurred at 0, like we're getting closer and closer and closer and closer and closer. Okay, so that's just with a sequence. Like if we can see that the terms are getting closer to a value. Maybe they're getting closer to something other than 0, and that's fine as well. It's just that they're getting closer to a value. So this letter, the sigma, so how to pronounce it, we have seen before when we have done integrals back in the day, when we kind of started with the infinite summation, and we said, oh, that's going to be an integral with adding on terms. And so that's what this is. We're going to deal with just these guys here, not the integrals this unit. And you guys are like, yay! Okay, so we're going to talk about this. The sigma, again, is adding up all of like the terms in a sequence. So a sequence is just saying that if I put like a summation in front of it, it means we're going to take the 5 plus the 8 plus the 11 and keep going and adding when I see the summation. So this would say that I would add up terms 1 through terms 10. So there's my starting and there's my ending. So I would add up term 1, 2, 3, 4, la la la, all the way to term 10, and I would get whatever that sum would be is what this would be equal to. Let's get a different color. Okay, so a lot of times we want to show that a sequence is decreasing in value because we're going to need that in order to show some converging things. So to show that we're decreasing is to show that the next term is less than, you could say less than or equal to technically, but less than the previous term. And that's monotonic is when this is a vocab, just when you're strictly increasing or strictly decreasing. And again, you can have the or equal to because you're technically not doing either, but we can count that as okay. Okay, so this one says, show that the following sequence is always decreasing for n greater than or equal to 1. So we could take and say that the next term is always smaller than the previous term. Or we can kind of, let's just write out some terms first. Let's start with 1, so that'd be -1. Go to 2, that'd be -4, because the negative's on the outside, which means I would like square, then negate. That's different than if the negative was on the inside of the square. Then I'd have to negate, then square. Okay, so then we could keep going. 3, And we can see that they are always decreasing, but this wants me to actually show that they're decreasing. So we have a couple of ways that we can do that. We can say the next term would be n plus 1, and that was squared, and I want to show that that's always less than just that original. So I'm going to square this out. Foil. I foiled your pen. Okay. And then we have that. Then I'm going to go ahead and negate. Oops. I think I have, I was like, I think I remember how to do that with this pen. It's my first time I'm using this pen to make videos because we're trying to make sure that they don't have that lag. That was horrible. Okay, so then these guys cancel each other. So we're left with this negative 2n minus 1 is less than 0. Negative 2n, and then I'm going to go over here. So n would be greater than negative 1/2, which is true for n greater than or equal to 1, because we said that from the beginning. So we are good. We have shown it. We have completed what it asked me to do. So let's do another one. Let's do B. Do B, do B, do. So we're going to take and we're going to plug in that n plus 1 into my n and show that that is always less than the original. So I'm going to go ahead and flip. And since n is greater than or equal to 1, I know that I'm not changing the sign here because that's going to be a positive number no matter what. So I don't have to worry about changing the sign and multiplying by a negative. So this would be 2n plus 1 is greater than, I'm going to distribute and multiply it over. So that would be 2n plus 2 plus 1 would be 2n plus 3. Those guys cancel. And look at this. That is a true statement. So this is a correct thing to say that we are decreasing for n greater than or equal to 1. Okay, let's go do part C. So I'm plugging in the n plus 1 everywhere I see an n. So the next term is smaller than the previous term. So I am going to go ahead and cross multiply. And I'm going to say that this is n. I'll go ahead and FOIL this out and add the 1. And I'm going to FOIL over here. So I'm going to keep going. And cross out where we can, kind of get it simplified. I'm going to get 0 over here, and this would end up being n squared plus n minus 1 when I brought all this over. And then this one's a little bit harder. When we get into those, I like to use graphs. So here at 1, I can see that if I plug in a 1, because I want to look, remember where n is greater than or equal to 1. So I've got some kind of parabola going on. And at 0, I mean, we can help out. At 0, we're at negative 1. So we can kind of get a better idea. You could even go find the vertex if you wanted. But I'm just getting a rough sketch of what's going on. So plug in 1. And what do we get out? 1, 1 minus 1. So we get out a 1. You could plug in a 2 and see what you get out. So that would be 4 plus 2 minus 1, so 6, so 5. So up here at 5. So I can see like the parabola did something, la 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 la, but we're looking, let's see, for where n is going to be greater than or equal to 1. Oh gosh, let's redo that. I can do better. Okay, there we go. So greater than or equal to 1 is going to be up here. And so if I look at that, I can see that we are, this graph right here is greater than or equal to 1, because there's my 1, when we plug in values that are 1 or bigger. So this is true. So all of those were decreasing. Okay, this is so much fun. This is factorial. So if you see this, it doesn't mean 5, oh my gosh, 5. It means 5 factorial, which is the same as multiplying 5 times 4 times 3 times 2, all the way down until you get to 1. You just keep subtracting. So 5 factorial is actually a numerical value that we could multiply out and get. So here, kind of simplifying though, let's say that I had 10 factorial over 9 factorial. Well, 10 factorial is 10 times 9 times 8 times 7 times blah, 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 times 1. But what is that piece right there the same as? So I could actually just kind of pull out a number from the factorial, and then this piece that's left is now 9 factorial. So I could say it's 10 times 9 factorial would be 10 factorial. So then we still want that over 9 factorial. So those could cancel out and we would have 10. So instead of actually multiplying it out, we're trying to do something easier. So let's look at this. This n plus 1 factorial is n plus 1, and then subtract 1 from that, and we'd have n. And then subtract 1 from that, and we'd have n minus 1. And then I am going to stop and put my factorial here instead of continuing to pull things out, because this is where we match here. So I'm going to have over n minus 1 factorial. And now those can cancel, and I'm left with n plus 1 times n. And you can FOIL that out if you distribute if you want. Okay, so now I'm just saying, what if I put a summation term in front of it? Well, just do the same thing, except for you just have this going along with it. But now it looks like this is a, 2n plus 2 factorial. So we're going to take the 2n plus 2. Let's subtract 1. 2n plus 1. Subtract 1 from that. And now we're at 2n. I want to match, so now I can end the factorial, and those guys will match. So now I have 1 over that 2n plus 2 times 2n plus 1. And this is going to be an important thing that we know how to do once we get to these summations and we do more things with them. So why don't you see if you can simplify this one to try to match and see if you can get that. So you can pause me and try it and then unpause me. So this was a 3n minus 3. That's where I've got them to match. Sometimes you're going to simplify on the top, sometimes you're going to simplify on the bottom. So now those go away. And I have this summation of the 3n times 3n minus 1 times the 3n minus 2. And that would be my answer. So that's the simplified version. And again, we'll see what those things do once we actually get into the heart of this. Okay, so just some fun review here of, you guys are like, fun, what? Okay, so review of some exponential rules. So here we are going to multiply. When we multiply the same base, then we can add the exponents. When we divide, we actually subtract. Power to power, multiply. Okay, so when we have that power to a power, then we multiply those two. Don't forget, if you have a negative exponent, you can flip it to the bottom and make it positive. If it was negative on the bottom, you could flip it to the top and make it positive for just the exponent, not the coefficient or anything. Anything to the 0 is 1, except for 0, because 0 to the 0 is indeterminate. Okay, so let's look at some of these together. Wonder if, no, I kind of want to make sure this is recording before I go further. My Screencastify video, how do I know this? Oh, I have a picture-in-picture. I didn't know that was happening. Such new stuff. So, okay, let me just see what happens if I hit stop.